In this lesson, we're looking at a couple of different counting methods. Sometimes we have a lot of things happening, events happening, and we want to know what are the total number of different outcomes that we can have, or the results from these. There's a handful of ways we could do this. If we want to know, what are all the outcomes of how many different ways can we choose something, we could just make a list. But sometimes when we make those lists, we aren't maybe consistent, we're not doing it systematically, we might miss an outcome, or maybe an outcome gets counted more than once, especially as the numbers get a little bit bigger. So what we want to do is we want to look at a couple of systematic ways to do this. And these first couple examples are going to use a table method, okay? We don't have to make a table, it's just one useful way to organize the information. Our first problem says find the number of two-digit numbers that can be formed from the digits 1, 3, 4, and 7. So what I'm going to do here is I'm going to put my first digit along the columns, and then, along the rows, and then my columns are going to be the second digit, or you could number these the tens place and the ones place. It doesn't really matter. And then I'm going to put my options here, 1, 3, 4, 7, and 1, 3, 4, 7. So then this chart on the inside here, okay, this part right here, gives me a way to organize all of the different outcomes. So I'm going to do the first digit is a 1, second digit is a 1. So my first number is an 11, and then I can have a 13, and a 14, and a 17, okay? And then going to the next row, 31, 33, 34, 37, and then the next row, starting with a 4, my 40 options are 41, 43, 44, and 47, and then 71, 73, 74, and 77. So my question says find the number. So this is a how many question. So my answer shouldn't be a list, it should be a number, okay? So my question is how many of these are there? And I can see we've got a 4 by 4 square. There are 16 different two-digit numbers that contain 1, 3, 4, or 7, okay? So it's not a super tough one, and really that's one that we could probably list and be fairly unlikely to miss things. But just in case, we have this systematic way to do this, and this would be really useful, especially as the number of things we're choosing from gets a little bit bigger. One thing I want to point out here is that there weren't any restrictions other than just using the digits 1, 3, 4, and 7. If we change it and say, okay, we can only have odd numbers, well, that means it doesn't mean we can't use 4s, but it means we can't end in a 4. So then everything in this column right here would get eliminated, and we would have to subtract that column. Or maybe it says you can't have any two-digit numbers where the same digit is used twice. So that would get rid of this diagonal, the main diagonal here, 1, 1, 3, 3, 4, 4, 7, 7. So if we have restrictions, we do need to take those into consideration. But in this case, we did not. Okay? Using a table for another example here, it says how many ways, so again, how many, a numerical question, okay? Can a president and a vice president be chosen from a club containing, and then our club is the set of Grant, Jason, Lindsay, Nick, Parker, okay? We have 5 options, 5 different names here. I'm going to put those into the table the same way we did before. So I'm going to put the president along the rows, and then the vice president up here as the columns. Sorry, not a great pen. Okay, and I'm also going to abbreviate. Conveniently, none of these 5 people have the same first initial, and also conveniently, they're already in alphabetical order. That was on purpose. So I'm going to use a G for Grant, J for Jason, L for Lindsay, N for Nick, and P for Parker. And then same thing here, Grant, Jason, Lindsay, Nick, Parker. So then, like I did up above, I'm going to pair them together as president and vice president combinations. So, but can I put Grant there? Okay, well that is, that's not going to erase. That right there is something that I need to think about, okay? In this situation, is it possible for Grant to be both president and vice president? Probably not. So really, I can go ahead and get rid of this right now and everything along this main diagonal because all of those are the same person matching with themselves. It's really unlikely that the club's going to elect the same person to 2 positions. So we can go ahead and eliminate that now. It wouldn't hurt if I had written GG and then gone on from there, but I would have to go back and get rid of those. So I would just be not counting those 5 spots. Okay, so moving on here, we've got Grant Jason, Grant Lindsay, Grant Nick, Grant Parker, and then Jason Grant, Jason Lindsay, Jason Nick, Jason Parker, Lindsay Grant, Lindsay Jason, Lindsay Nick, Lindsay Parker, Nick Grant, Nick Jason, Nick Lindsay, Nick Parker, Parker Grant, Parker Jason, Parker Lindsay, and Parker Nick. Okay? So now, again, the question is how many ways? So I'm looking at this right here, and I have a 5 by 5, which gives me a total of 25, but remember we took out this main diagonal, so we can do 25 minus 20. Oh, sorry, jumped ahead myself. 25 minus 5 to get a total of 20, or we could just count all of the boxes that have something in them, and we would get 20 either way. Okay, now, second part of this question says, what if 2 co-chairs are chosen instead? So let's look at the difference between a president and a vice president and 2 co-chairs. There is a difference between being the president and the vice president, okay? I'm pretty sure country leaders would tell you they might prefer one over the other. There's definitely something that distinguishes the president from the vice president as far as, responsibilities, power, whatever, probably salary. But if we talk about 2 co-chairs, the implication there is that we just have 2 people in a leadership position, and it doesn't really matter which one is which, okay? Or it doesn't really matter which one we name first. We're not saying that it doesn't matter if you're the co-chair or not. We're saying that if I'm naming Lindsay and Nick as the co-chairs, it doesn't matter if I say, hey Lindsay, hey Nick, you're co-chairs, or hey Nick, hey Lindsay, you're co-chairs, because I've named the same 2 people. It doesn't matter whose name I say first, okay? So what that means is we need to get rid of some of our outcomes because they're the same. So for example, I see, let's switch colors here, okay? So I see Jason and Grant here, and Jason and Grant here, and it says Grant and Jason, okay? The outcome there is the same if we're talking about co-chairs. So really, I would want to get rid of this, okay? And then again, I see a Lindsay and a Grant and a Lindsay here. If they're co-chairs, that's the same outcome, so I want to get rid of this. And then here we have Lindsay and Jason. Well, Jason and Lindsay are here, so I want to get rid of this. And what I find is that I'm actually going to eliminate half of my table, okay? So I could look at it as kind of like a bottom left triangle and a top right triangle, and I would be eliminating one of those. Doesn't matter which one, because we're just talking about counting the number of outcomes, but we don't want to count all of those twice. So we don't want to count Nick Lindsay and Lindsay Nick as 2 different outcomes. So now we can either take 20 and divide it by 2 because we know we just got rid of half of our outcomes, or we could recount what's in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we see 10 outcomes if we're talking about co-chairs instead. So that's something we need to pay attention to. Not just are there any restrictions, but does the order that we name things make a difference? Do we have any duplicates in our table? If so, we need to get rid of those, okay? All right, next method is making a tree diagram, okay? Here we have 3 coins that are being flipped. The outcome for each coin is going to be heads or tails, and maybe right off the bat, if we look at this and say, okay, well, 3 coins, each can be head or tails, maybe there's 6 options, okay? A tree diagram is going to give us a way to list all of the possible outcomes, and we are going to see that maybe our first instinct was wrong. So, making a tree diagram, I'm going to do this kind of branching sideways. I'm going to start with my first event, which is the first coin flip, and then list the possible outcomes, which are going to be a head or a tail. And then moving to the side, my second outcome, and I'll go ahead and put my third outcome, or my third event, sorry. And then the second outcome can also be a head or a tail, but really there's a difference between getting a head after a head and a head after a tail. Okay, so I don't just want to put head tail under the second event. What I want to do is branch from each of the outcomes on the first flip, okay, and list a head and a tail as the possible outcomes for the second event off of each of those. So really, I have 4 outcomes now. I have a head followed by a head, and a head followed by a tail, and then a tail followed by a head, and a tail followed by a tail. Now, here, does the order matter? Is a head then a tail different than a tail than a head? If we're looking at the number of different outcomes, yeah, we do need to consider those differently, okay? We're not talking about probability just yet. We're going to get there. But if we were thinking about probability and we didn't list those as separate outcomes, then the probability of getting one head and one tail, we might say, is just 1 out of 3 if we didn't count these 2 branches separately. But really, it's 2 out of 4, okay? So we do need to list those separately. All right, and then last, for the third event, again, we have head-tail options for each of these. And sometimes it tends to get a little bit squished, but that's okay. We'll fit everything. Just move downward. Head, tail, and head, tail. Okay, so how many outcomes do I have? Well, I have a head followed by a head followed by a head followed by a head followed by a tail, head, tail, head, head, tail, tail. Okay, so I can see that each of these branches, or full sets of branches here, is representing a different set. And so I could just count down here, how many possible outcomes do I have? There are 8. There are 8 possible outcomes, okay? So yeah, our 6 would have been wrong. It's a good thing we actually listed them and didn't just make assumptions, okay? So that's a tree diagram. Anytime you have something that maybe there's more than one event happening, maybe you are, there's a spinner that has 5 different regions marked A, B, C, D, E, and then there's a die that's being rolled with a 1 through 6 as an outcome. Maybe we want to list all of our possible outcomes using a tree diagram instead of trying to just, write down a list where we might miss something. So that's another systematic way to organize things. I wouldn't recommend doing that if you had, 20 different outcomes for each of your 3 events, but it works nicely for things that have smaller numbers of options, okay? Speaking of dice here, this is a table of rolling 2 dice and the possible outcomes here. It's called a red and a white die. That just happens to be the picture that I found. And a lot of questions about probability and numbers of outcomes and counting methods involve dice because they're nice, independent events. Rolling something on the first die doesn't affect what you could possibly get on the second die. If you get a 2, you still have an equal chance of getting a 5 on the second die as if you had rolled a 3 on the first one instead. That doesn't really matter. So I would really recommend that you keep an eye on this chart, maybe keep it out while you're doing homework or on a quiz. It's not something that you would have to have memorized or recreate on a test, okay? If it's necessary, then it would be provided for you. But it is really useful to look at because it's already listed and we can quickly count outcomes for whatever we're looking for. So for example, if the question was how many different rolls have a 4 in them, okay? And we can quickly see 1, 2, 3, 4, 5, 6, 7, 8, 9, don't count that one twice, 10, 11. So there's 11 different outcomes that have a 4 in them. Or maybe the question is, how many of them have a sum of less than 5? So then we can say 1, 2, 3, 4, 5, 6 of them have a sum of less than 5. It's a lot easier to count those kinds of things when we're looking at all 36, make a note of that here, at all 36 possible outcomes instead of having to recreate that chart every time. So again, I recommend that you keep that with you.